Hello, Pradeep. Are you there?
Yes, sir, I'm there. Yeah. Good evening, sir.
Good evening. You can see the screen, right?
Yes, sir, I can see.
Okay. So we'll wait for like couple of minutes and we'll start.
Yeah, sure. Sure, sir. Yeah.
Okay. Yeah. So we'll start. Mm, the thing is, today we'll discuss about dimensional analysis, and this topic you might have studied earlier also because I think it is part of your 11th, 12th syllabus as well. But there only you study about fundamental units or fundamental dimensions, then derived dimensions, dimensional homogeneity, and what else? Uh, you know, you don't study the advanced concepts like uh, this Buckingham Pi theorem or this model prototype uh, methods, like how to develop a model. How to develop a prototype for a model or whatever you want to call, but uh, replica of certain physics that you want to derive in order to save your time, money, and efforts. And there also dimensional analysis helps. Then there are some non-dimensional numbers like Reynolds number, Froude number, Weber number, etc., Mach number, and there are like a lot of more numbers also there which are not part of this course, but uh, like because this is a fluid mechanics course, we are not considering thermal interactions like heat transfer or conduction, convection, like that. So there various non-dimensional numbers come into picture, like Nusselt's number, uh, Prandtl number, and if you consider another domain which is like mass transfer, there one second, Pradeep, you have posted one question.
We'll do later on, sir, after discussion. Just I have some doubt in these questions.
Okay, we'll take it up later.
Later, sir. Yes, just later.
Yeah, so then like in mass transfer, which we typically don't study, there are different numbers like Sherwood number and mass diffusivity, etc., etc. Mass diffusivity is not a dimensional number, but Sherwood number is there, and one more number is there. I'm forgetting it. Schmidt number is there. Anyway, so we'll start. So basically, before doing anything, oh, one second. So first of all, the basic question: what are the fundamental dimensions? This question may sound like very trivial, but it's not. Uh, Many people don't know or don't remember these things when they grow up or they study higher concepts, but these are actually very important things. And as the name suggests, when I say it is a fundamental dimension, that means it is non-divides. Like you cannot divide this quantity into another combination of two quantities. So that is what its fundamental means. Like it is the like basic building block of all other things. So there are like in our course, we'll typically deal with mass, length, and maybe time. But there are like total 6-7 fundamental quantities. We'll just list them down here, maybe for your revision. Here we'll use capital M for mass. Then there is length. We'll use L symbol. Time, we'll use capital T. Then there is temperature. Since capital T is taken for time, we'll use theta for this if required. Then there is current. Generally, people use A for it because I is its symbol only. Then there are like light intensity, candela, and then there are like mole, so quantity, etc. So for these are not our like they are not pertinent to our discussion today. So let's leave them as it is. But you should be at least aware of mass, length, time, temperature, current, because they are uh, important, and all other physical quantity dimensions can be derived by some combination of these fundamental dimensions. So that is why they are called as fundamental. Then we'll just go through some of the dimensions of some of the relevant the relevant uh, relevant physical quantities. So basically, whichever we'll be using today, I just want to note them down initially only so that later we can refer back if required. So first is mass, mass is already done. Velocity. So I'll write unit in the bracket. So therefore its dimension should be meter is L, second is T. So since it's a division, and acceleration meter per second square. So only one we'll not use curly brackets for it. We'll just keep it as it is. Maybe later we can decide on it. So these are like simple things. Then there is important thing which is force. So force is nothing but mass into acceleration. So mass is kg and acceleration is kg per meter square. So this becomes mlt minus 2. Now there is important concept of energy or work or heat. All these things, like all these quantities, they basically define energy. And energy, its SI unit is joule, but if we know that energy is force into displacement, that means uh, so in force formula you just multiply with displacement, so m become m square and remaining thing is same. So this becomes ml square t minus 2. So that is there. Then there is something called as power. Power is nothing but rate of this thing, what you say, rate of energy change, or maybe force into velocity. That way also you can define it. So that case, its unit becomes kg meter square s minus 3, because it is a rate at which you do the work or energy spent. So therefore, it becomes ml square t minus 3. Then there is pressure or stress. It is nothing but so unit should be Newton per meter square, right? So Newton is basically this. Like I'll use this term equivalent to. So Newton is kg per meter per second square. So if you divide it by meter, so it becomes kg minus 1 and s minus 2. Because I hope there is, if you have any doubt here, you can ask. But I think if we had gone through the course material, these things will not be much difficult for you to understand. Even if there is some doubt, you can stop me and ask. Then there is one important quantity that we'll be using today. So therefore, let's get its unit done. So that is called as dynamic viscosity. And typically it is denoted by mu. Its unit are, you know, what are the units of dynamic viscosity? How would we calculate that? Can anybody tell me? Anyone? Pradeep or Hardik, are you there?
Yeah, we are here, sir.
Yeah, so see, basically the point I'm trying to make is I don't remember the units. So, and you should also not, because that is not the right way to go about it. So, if anybody asks you what are the dimensions of dynamic viscosity, so the basic, like, simple idea is to see any formula where the dynamic viscosity is involved. So, we know that, you know, this in fluid mechanics, this Newton's formula is there. So it is typically goes something like this, right? Tau equal to mu by du by dy. So this tau is nothing but the shear stress, and mu is the dynamic viscosity, and u is the rate of change of velocity along that direction. So from here you can see tau is stress, right? So we have the dimensions for it, which is just here only, pressure, stress, they have same dimensions. So there will be ml minus 1t. Then we'll have some dimensions for mu. And now velocity we have meter per second, and it is divided by meter. So that meter will get cancelled, and it will be just time inverse. So t minus 1. Therefore, dimensions of mu will be, so when this will go here, it will get multiplied, and it will be m l minus 1 t minus 1. or like this is basically kg per meter per second. So like that you can like you can't remember all of this because that's not humanly possible. Maybe right now you are remembering it since it's a ongoing discussion, but like for later, I'm telling you the thing that you should remember any formula in which that unit is involved, and you derive it from there. So then there is, since we are discussing dynamic viscosity, there is something called as kinematic viscosity. Generally they denote it by nu, and for this also we have the formula that nu equal to mu by rho. So therefore, if you want to find the dimension of nu, what are the dimensions of mu? We just derived m l minus 1 t minus 1, and density is nothing but kg per meter cube. So kg is m and meter cube is l minus 3 because it's per meter cube. So therefore, the dimensions of nu become L square t minus 1, which is nothing but meter square per second. This is very important, this thing, because in fluid mechanics you have kinematic viscosity, and if you study uh, the heat transfer, where you have uh, something which is called as alpha, thermal diffusivity, they call it there. So I'll just maybe you are not aware of this, so I'll give you the formula. I just wanted to prove one point. So there is something called as thermal diffusivity. Diffusivity. It is typically denoted by alpha. It will come into the heat transfer course if you have not studied yet. Don't worry about that. But the point that I wanted to make was this: it is typically denoted as K by rho Cp. Now, here if you want to find its dimensions, first you need to know what is K and what is the dimensions for Cp. So let's do that. Maybe what I'll do, first we can look into K and Cp, then we can go to the thermal diffusivity part. There is a reason why I'm going out of the fluid mechanics domain. Just hang on a second. So let's say,
Sir, for viscosity, sir, once you know the final unit, like meter square per second or kg per meter per second, then we can just directly write, sir. You don't need to derive so many things, sir. Is it not? Like kg is equal to m, this m mass, then m is equal to uh, that, this. Yeah.
yeah, I see. This is like a basic template for our today's discussion. So later when we'll solve some problems, I'll not derive everything. I'll just refer back to these dimensions. So therefore, I'm writing everything here, even if it's not needed.
So,
Uh,
yeah.
so okay, let's do the thermal conductivity first. It is typically denoted by Ka, and now I don't remember thermal conductivity formula, neither I have any reference for it in front of me, but I know there is a like conduction of heat formula, which is nothing but Q is equal to K, and if you want to put area also is there, and then there will be some dt by dy. If you don't know this, that is also fine, but this is like very uh, commonly used formula in conduction. uh, I think it is called as Fourier's law of conduction. So basically flux is proportional to the temperature gradient, and that proportionality constant is your thermal conductivity. So the Q is heat. So therefore, what is the for dimensions of heat? It is ml2 t minus 2. So ml2 t minus 2. K we need to find out. A is the area, so it will be L square and T by what do you say? This is dt by dy, so temperature gradient. So it will be temperature is nothing but theta, and this is L because it's just a length unit. So if you do that, therefore you get K as a uh, 1 second, M L T power minus 2. 1 second. Oh, this is not energy. This is uh, uh, power, because this is conduction, right? So we talk in terms of power. So therefore this will be minus 3 and theta power minus 1. Okay. Don't, if you don't want to study thermal conductivity here, that is fine, but just I'm giving you some basic concepts. Then there is a specific heat capacity, which is called as Cp. So here also I don't know the formula, but I know Q is equal to, let's call this as Q dot because it's a rate of energy, but typically we know Q is equal to mCp delta T, right? So here Q is, here it is energy, therefore m L square T minus 2, mass is only capital M, Cp is unknown, delta T is theta, therefore dimensions of Cp will become mm will get cancelled, and there will be L square T minus 2 theta minus 1. Okay, and now you can calculate the 1 second thermal conductivity or thermal diffusivity dimensions. So this will become 11th, and therefore dimension of alpha, what is the dimension of K, which is m L T minus 3 theta minus 1, and rho is kg per meter cube, so m L minus 3, and Cp is L square. Somebody is on speaker, can you mute yourself? I think E Budhevi. 1 second. E Budhevi, can you mute yourself, please? It is some noise is coming here. Okay. So if you solve this, if we have done earlier things correctly,
have been muted. You have been muted, sir.
Oh, when I muted all, I also got muted. Huh? Now it is coming.
Yeah, it is coming, sir. Yeah.
Okay, thank you. So there is a fluid, and for which the stress, which is sigma xy, is given by this expression, and now it is asked that what are the dimensions of uh, k. So what is the dimension of k? It should be what are the dimensions. Okay, so this question looks like scary something, uh, but there is nothing difficult here. You just go ahead as usual. So solution is, so sigma xy, which is a stress. So stress is nothing but having the dimensions of Newton per meter square. So
Force per unit. Yeah.
so it will be m l minus 1 t minus 2, and this k we have to find out. Now du by dx, so u is the velocity in x direction, so velocity is meter per second, so that is there, divided by 1 length. And for the second term, same, lt minus 1 divided by l, but it is raised to power n minus 1. So here ll gets cancelled, and what remains is, this side will keep it as it is, then this unknown k. Here one unit is t power minus 1, another unit is t power minus n minus 1. I hope there is no confusion that for any dimension, if it is raised to power 2, the dimensional representation also increases by that power. For example, if it is length, it will be L. If it is area, it is L square. If it is volume, it will become L cube. So therefore, this n minus 1 factor will just get multiplied with the t power minus 1, and it will come inside. And since it is tt, so this will become minus 1 minus n minus 1. So basically it will get added, and since both of them has negative sign, it is nothing but mm, 1 second, minus 1 minus 1. So here it will minus 1 will get cancelled, only minus n will remain. Therefore dimensions of k will become m l minus 1 as it is. This minus will go there and it will become plus, so it will become t into n minus 2. So like, I mean, I have taken some different type of example because typically you'll see straightforward questions, but sometimes this type of weird questions come, but no need to worry. You just follow your basic principles and you can get the answers. Then maybe one more basic question on dimensional analysis. 1 second. Yeah, so this might have been covered in class also, that this thing, there is something called as dimensional homogeneity. So basically, if you have any governing equation or any equation for that matter, if it is a valid equation, then the dimensions on the left hand side and dimensions on the right hand side for all the terms should be same. If they are not, then it's a inconsistent equation, and that is not the correct one. So for example, if you take our Bernoulli equation, then right, Bernoulli equation, uh, you know like 1 second, I'll just write it. This might have been covered in class also. So we'll not take Bernoulli. Maybe some other equation. Navier-Stokes you have not seen it, right? Because pipe flow is not yet taught, no? I mean, before.
Sir, one question here, sir. Basic question. Say, sir, why the stress became L minus 1 minus T minus 2, sir? Sorry for this. This is a small question.
Yeah, so here, so basically pressure and stress, this is sixth number. They both have the unit of Newton per meter square, right? Force per unit area. And force is nothing but mass into acceleration. So that's where, like, if you write it that way, mass will have m, acceleration will have meter per second square, and if you divide this product by meter square, you will get kg per meter per second square, which is ml1 t minus 2.
Yes, yeah.
So that is why I have written this in the starting, so that if anybody has confusion later, you can just go back to the front page and you can just see there. Okay, so okay, I'll not define the equation. I'll just write what it is. So for example, one second, is following equation dimensionally homogeneous? So this is the question, and the equation is something like this: density into del u by del t. This is velocity per unit time plus u dot gradient of u, or maybe let's take a simple case, del u by del x equal to minus del p by del x. Here p is pressure, and then there is this term called as del square u by del y square. So here rho is the density, u is velocity, p is pressure, mu is viscosity, and x and y are the length scales. So now if some question, like some equation like this is given to you, and if they are asking whether it is dimensionally homogeneous or not, so what you have to do, you have to take each term and check their dimensions. So we'll take first term, which is rho into du by dt. So this is the first term, right? So now what are the dimensions? For rho, the dimensions are kg per meter cube. So kg is m and meter cube is minus 3, correct? And del u by del t, basically rate of change of velocity with respect to time. So in the numerator, velocity units will come. What are the velocity units? Meter per second. So it will be L t minus 1 divided by time. Correct. So now this becomes m remains as it is. Let's say L cube remains as it is. The second term becomes L t power minus 2. Therefore, m, oh, this is minus 3. So it becomes minus 2 and t minus 2. Okay. So this is the first term. Now you check the second term. Second term becomes rho u del u by del x. There is a dot product here, but dot product is again like this thing, component wise multiplication, so it should not affect our dimensional analysis. So now again, rho is ml minus 3, u is velocity, so it will become lt minus 1, and del u by del x. So same as the previous, del x will be L, not the t here, because there was it is del u by del t, here del u by del x. So now if you solve this LL will get cancelled, M is still as it is, and there is one more L, so this becomes L power minus 2 and T power minus 2. So first and second term dimensions match. Now let's check this term, which is minus dp by dx. So minus plus sign will not affect the dimensions, right? It is just a like direction of that quantity, but dimensions are independent of direction, right? So if velocity or acceleration is positive or negative, it doesn't matter. The dimensions will be still meter per second square. So therefore, negative sign is there, don't worry. Here, numerator is x, so that will be L. And pressure. Pressure, we have derived the basic units. So pressure is 6 number. So pressure is ml minus 1 t minus 2. So this is ml minus 1 t minus 2. So if you solve, what you get, m remains as it is, L becomes minus 2 and t remains as it is. So this is also matching with the earlier two things. Now the last quantity, which is mu into del square u by del y square. So what is the dimension of mu? We derived it, right, somewhere behind. So mu is this one, 7 number. M L minus 1 T minus 1. So mu is M L minus 1 T minus 1. And now there is one important thing that you should remember. Whenever there is gradient operator, which is del u by del x or del u by del t, first order derivative, we just divided by L or T, whichever it is. But if it is a second order derivative, for example, this is nothing but del y by del u by del y. So therefore it is a second order derivative, right? So therefore in the numerator you can write velocity only because it is only coming once. So velocity is Lt minus 1. But denominator you need to write the length twice. So that becomes L square. So if it is like third order derivative or fourth order derivative, that way you have to divide by L cube or L power 4. Okay. So then if you solve, m remains as it is. Here one L get cancelled and another L will become minus 2, minus 2. So see, if you notice, all the four terms have the same dimensions. So this is a dimensionally homogeneous equation. And since dimensions of all terms match, this equation is dimensionally homogeneous. Actually, this equation is nothing but Navier-Stokes equation, and it is a conservation of momentum equation. I just written it for a simple 1D, not 1D actually, simple case, not all the. So basically, this equation you'll encounter when you solve boundary layer problems later. There, this equation is used. And see, if you notice the units, it's m L minus 2 T minus 2, right? So in our earlier derivations, where did we get any m L minus 2 T minus 2? What is the force? M L minus 2. 1 second. M L minus 2 T minus 2. So this is nothing but the conservation of momentum equation. So now, 1 second. Like we can derive like dimensions of momentum also. We should have done that earlier, but we forgot there. It's okay. So momentum is
RHS, I think there is a minus It will not cancel out, sir. These two terms will not cancel out, is it not?
Which minus? This minus del P by del X.
Yes, sir. Yes.
No. For dimensional analysis, negative positive sign doesn't matter. You can understand it this way. Let's say, let's consider acceleration. So if your vehicle is accelerating, the acceleration will be positive, right? So that is one case. But let's say if you are applying brakes, your vehicle is decelerating. In that case, your acceleration will the 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 acceleration will have some negative value, but still the unit is meter per second square, right? Whether it is acceleration or deceleration, it doesn't matter.
I
The
got it, sir. Yes.
dimensions of pressure, whether it is positive delta P or negative delta P, it will still be Newton per meter square. So that's how. So the point that I wanted to make was this equation. Let me denote it by equation number 1. Equation 1 is momentum conservation equation. So now we'll see what is momentum. Like I'm saying, it is momentum conservation, but let's see whether it is matches with the momentum dimensions. So dimensions of momentum is nothing but mass into velocity. So mass will have dimensions of capital M, velocity L, t minus 1. But the units that we are getting here for all the terms are M, L minus 2, t minus 2. Therefore, basically what they have done is they have conserved this something called as momentum per unit volume. So if you do that, momentum is ml t minus 1 and volume is nothing but L cube, right? So then it becomes m L minus 2 t minus 2. So basically this is momentum conservation equation, but momentum per unit volume. And that is like in fluid mechanics, we basically consider one fluid element of some volume and then derive this equation. Therefore, this whole equation will always be in terms of unit volume. Since, see, basically you are taking density, right? So if you take density, it is always per unit volume. If in some other equation, if you take mass, then it won't be that way. But let's not go there. The basic point was this equation that we are seeing, equation number 1. You will see this later in boundary layer, and there it is basically a simplified form of Navier-Stokes equation, which is momentum conservation equation. And since it is written in the density terms, it is momentum per unit volume. So that is the key takeaway. And this is how you define you check the dimensional homogeneity of the any governing equation. I hope that is clear. Then so then there are two basic methods for dimensional analysis.
It should be negative minus 2, sir. Because earlier it was negative t minus 2. In this case, it is m not negative, sir, here. Right side. RHS. M L minus 2 t 2.
Oh, right. Understood. Okay. So basically, it is there should be one T also here, right? So see, ML. This is correct. ML minus 2, T minus 2. It should be there. So here there will be one T here, and then it will become minus 2, right? And where this T comes from, it is like there will be time. So basically, it is force conservation only, rate of change of momentum per unit time. So it is not only volume, it is time into volume. Yeah, because I mean this is extension of Newton's second law, which is they say no that force is nothing but linear rate of change of linear momentum. So So like if you go and see the derivation of Navier-Stokes equation, it is nothing but uh, it starts from the Newton's second law. They apply it to a small fluid volume, and then they derive different forces. So uh, this del P by del X is nothing but the pressure gradient across the X direction, and the other term mu del square U by del Y square is viscosity term, basically viscous drag, sorry, not drag, viscous dissipation term. So yeah, thank you for pointing out. It's not only momentum per unit volume; it's rate of change of momentum per unit volume. So that is nothing but the force conservation. But typically they call it as a momentum conservation equation for fluid, Navier-Stokes. Because otherwise, if I don't take time in the denominator, the units dimensions won't match, right? So that is actually incorrect. Yeah, I should not have done that. But anyway, so maybe if you don't understand this Navier-Stokes and other things right now, it's okay. We'll revisit them later also. But for this discussion, the main thing is you should know how to check the dimensionality or dimensional homogeneity of the any governing equation. And the way to do that is check the dimension of each term in the equation, whether it is on left hand side or right hand side, doesn't matter. And then if all the dimensions matches, then only it is a dimensionally homogeneous equation. Otherwise, it's not a valid equation at all. So moving on, there are like two methods. Actually, there are more than two, but for our course, there are two methods for dimensional analysis. One is called as Rayleigh's method, and one is called as Buckingham pi theorem. Based on that, there is one method. Rayleigh's method, we can take one example. One second, let me just see the question. If I okay. Yeah, so maybe this is one second. I'll take some other example. This is a difficult one. Maybe we can take it later. Since we are introducing to the Rayleigh's method, so we'll start with simpler one if it is there. 57. Yeah, okay. So it is given that there is one orifice meter. Okay, for an orifice meter. So from our previous discussions, you might remember that orifice meter is a flow measurement device. So it is given that for an orifice meter, the flow rate, volume flow rate, is given as some constant K into density raised to power A, viscosity raised to power B, pressure gradient raised to power C, and there is some function of small d by capital D raised to power, let's say, E. So here small d is diameter of orifice meter and capital is the diameter of pipe. So basically small d is less than capital D. So like this question is there, and we need to find the A, B, C and E. So these unknowns are to be found. I have not given you whole complete write up of the question because that way it will become too, like it will take too time for me to write, and I'm just giving you the jinx. So here you can use the Rayleigh's method. Rayleigh's method is actually like it can be used for a simple problems where there are not lot more complexities and not lot more independent variables, etc. So for simple problems like this, you can use the Rayleigh's method. There are like limitations of Rayleigh's method. I'll explain them later. But right now, just we'll see how Rayleigh's method works. 1 second. So yeah. So before going there, let's start. So what is typically done in the Rayleigh's method is so you write all the dimensions for each and every one quantity like in the equation form only. So volume flow rate is nothing but meter cube per second. So meter cube is L cube and per second becomes T minus 1. So this is our left hand side. K is a dimensionless constant, so let it be like this. Density has the unit of kg per meter cube raised to power A. This is A. Mu has the unit of kg per meter per second. Sometime back only we did that, so it will be like this. Pressure difference is nothing but expressed in terms of pressure only. So that is ml minus 1 t minus 2 raised to power c. And yeah, then again there is this confusion that what is the unit of this function of small d by capital D, right? But you know it really doesn't matter because uh, this E, okay, so basically this d by d, so if you check the dimension of small d by capital D, they are dimensionless, right? Because meter by meter, so any function of dimensionless number is also dimensionless, so there is no dimension for the last term, so to the power E. So here there is, okay, let's solve the question and then we'll see what is there. So now we compare the powers of all the dimensions. So comparing powers of fundamental dimensions. So first fundamental dimension, let's take M. So on the LHS there is no M because volume flow rate doesn't have any M. But on the RHS, first term has kg and it is raised to power A. So since we are comparing powers, second term also has one M raised to power B. Third term also has M raised to power C. And E, there is no units for that. If you compare L powers
So
of
this step is not clear, sir. This step is not clear. Sorry. It's M, sir.
It's okay. Yeah, it's okay. Don't say sorry. Okay, maybe I should not skip one step in between. I'll just write the whole thing. So okay, so this side remains as it is. Dimensionless k parameter is there. So now you multiply like m raised to power a, l raised to power minus 3a, right? First term. Just take the a inside the square bracket. This becomes m power a, l power minus b, t power minus b. Third term becomes m power c, l power minus c, t power minus 2c. And fourth term is anyway 0, so leave it there. Now you club them together. So whatever m terms are there, this should be b, sorry. So a plus b plus c. And for L, first term is minus 3a, second is minus b, third is minus c. And for t, there is no t in the first term on the RHS, only minus b and minus 2c are there. Is this okay?
Yes, sir.
Yeah, so and on the LHS I can just write it as m power 0, L power and t power minus 1. Correct, because m power 0 is only 1. So now you compare the powers of m, l and t. So that is what I have written here, comparing powers of fundamental dimensions. So fundamental dimensions here are m, l, t. So for first, let's compare power of m. So on LHS it is 0, but on RHS it is m raised to power a plus b plus c, right? So that is what I have written here. And for L similarly, on LHS it is 3 because it is L cube here. And on the RHS it is minus 3, minus b, minus c. And for T it is minus 1 on the LHS, and on the RHS it is minus b, minus 2c. Okay, minus b, minus 2c, minus 1. Yeah, so this is nothing but if you take b plus 2c equal to 1. Okay, so now we have 3 unknowns and 3 equations, so we can solve them, right? So you do one thing, you write as how should we solve them? Yeah, we can, let's number them. Let this be 1, 2 and 3. First you add 1 and 2. If you add 1 and 2 equation, what you get? 0 plus 3 is 3, and a minus 3a, it becomes minus 2a, and b and c get cancelled, right? So therefore a becomes minus 3 by 2. So now you got a. Now put a equal to minus 3 by 2 in equation 2. So now what you get? 3 equal to minus 3 into minus 3 by 2 minus b minus c. Therefore 3 is 9 by 2 minus b minus c. Therefore b plus c is 9 by 2, which is 4.5, minus 3, which will become 1.5. Therefore b plus c is 1.5. Let's take it as equation 4. Now you have equation number 3 and equation number 4, which only contains b and c. So now what you do? You subtract 4 from equation 3. So in that case, what happens? Equation 3 is b plus 2 equal to 1. Equation 4 is b plus c equal to 1.5. You subtract the second equation, right? So what you get? bb gets cancelled. 2c minus c is c. 1 minus 1.5 is minus 0.5. So you get c as a minus 0.5. And we know that b plus c is 1.5 and c is 0.5. Therefore, B is 1.5 minus C, and C is minus 0.5. Therefore, your B becomes 2. Okay, so now final solution. Therefore, final solution A equal to 1.5, oh, minus 1.5, sorry. B equal to 2, C equal to minus 0.5, and E cannot be determined. So, I mean, there is no information given for us in order to determine the function, which is d by d power e. So, we can't say anything about e. E can be anything, but we can concretely say that a, b, and c are these values, and therefore, finally, you can write your flow rate as a just write the values there. So, one dimensionless number is k, density power minus 1.5, then viscosity power b, which is 2, then delta p power c is minus 0.5, and then there is some function of d by d power e. So this is your final one second, yeah, so this is your solution. So this is Rayleigh's method. Rayleigh's method, what you do basically on LHS and RHS, you write the dimensional equations and you reduce them to a condensed form, and then finally you compare the powers of the fundamental dimensions, and then you get some set of equation, and then you solve them, and then you get the functional relationship between the variables. So here Q is your independent variable, which is flow rate, which is not like it is independent. No, it is dependent on other four functions. So there is one concept of dependent and independent variable. So here Q is dependent variable since it depends on density, viscosity, delta P, but delta P, density, mu are independent variables. Independent means if I am doing some experiments, I can change mu, density, and delta P. Uh, that change is in my hand, so they are independent of each other. But the flow rate that I'll get finally is dependent on what value of mu, rho, delta P I choose. So therefore, it becomes dependent variable. So this is how the Rayleigh method works. Now, advantage of Rayleigh method is it is very simple. You just have to write the dimensions and compare the this thing, compare the new powers of the dimensions. But the disadvantage is it is applicable, or it is useful if your number of variables is not very large. For example, here number of variables are only 4, rho, mu, delta, p, q. But let's say I have some, like, let's say limitations of Rayleigh's method if number of variables become greater than number of fundamental dimensions. We cannot solve the system of equations. So what I mean by that is, so here basically we had 3 equations, right? equation 1, 2, 3, and we solved them and we got the unique solution. But what if, like let's say this d by d, instead of d by d function of d by d, if I just gave you some another parameter such as let's say thermal conductivity, so that will become k power e, right? K raised to power e. And then there are four unknowns a, b, c, and e. But you only will have four equations. Oh, if you take conductivity, then thermal temperature also comes in, but let's not go there. My point is, if you have three equations and five unknowns, is it solvable? Pradeep?
No, sir, no.
No, right? Because that is not the that system of equation will not have a unique solution. So this Rayleigh's method will work only if your unknowns or your total number of variables are equal to or less than the fundamental dimensions.
So fundamental dimensions means mass T and
Yeah. So the
three,
initial
three that means
7
you need to say three, sir. 7.
total are 7, but in this problem only MLT are coming, na? kg,
Yes, sir.
length, and the time. In some problem, temperature may also come. So there it will become 4. Fundamental dimensions will become 4. So if you have 4 unknowns and 4 fundamental dimensions, you can still use Rayleigh's method. But if you have 5 unknowns and 4 dimensions, you can't use it, because then the system of equation becomes unsolvable. So that is the limitation, and that is where the second method, which is written as Buckingham Pi theorem, which is based on Buckingham Pi theorem, comes into picture. So we'll go to the Buckingham Pi method, because that is actually very commonly used method also. So what does Buckingham Pi, it should be Buckingham's Pi theorem, but okay. Buckingham Pi theorem, what does it say? Anybody knows? Pradeep, any idea?
So the number of variables, the number of dependent variables minus the basic variables, fundamental variables, that gives rise to Buckingham, like the number of independent variables. My point is, like there are 4 or 5 variables, there are 6 variables, minus 3. 3 is the length, mass, and time. Then there are 6 minus 3. Then the 3 are the independent variables.
Yeah, you should not call them independent variables. They are the pi terms basically, or they call it
Yes.
as repeating variables, but that is confusing. So just say that 6 minus 3 is 3, na? So there will be 3 pi terms, and you can define or get the solution if you define 3 independent pi terms. And how to define that? There are like certain rules. For example, each pi term will be dimensionless, and then let's say if you have 3 pi terms, because you said na 6 minus 3, it becomes 3. So you will have pi 1, pi 2, pi 3. So there is always one dependent quantity in your problem, right? For example, here the volume flow rate, which is Q, it was dependent property, and all others are independent. So okay, I'll write, maybe this is confusing. So let's say I have a problem in which force is some function of density of the fluid, viscosity of the fluid, length of the plate over which the fluid is flowing, and let's say pressure gradient across the plate or the length, or what else? Let's say thermal conductivity also. Uh, just for the timing I am taking. This may not be real problem. This is just for the illustration purpose. So I want to find a function of function for force acting on a plate of length L, and it is dependent on density, viscosity of the fluid, K and Cp of the fluid, and length and the delta P across the plate, or the whatever problem that I have in my head. So here these are called as independent parameters. Okay, and this force is dependent on all of them, right? This is called as dependent parameter. So what Buckingham Pi theorem says? So here dependent parameter is 1 and independent parameters are 6. So total parameters are, one is dependent and independent are 6, so 7. And then total fundamental dimensions. So now here, since we have taken thermal conductivity also, thermal conductivity has temperature in its dimension. So if you go back to the starting of the class, so for thermal conductivity, yeah, so 9 number. So thermal conductivity has the dimension with m, l, t and theta. Theta is for temperature. So therefore there will be 4 fundamental dimensions in this problem, which we have defined here. So Buckingham Pi theorem, what it says is, if you have such a system of physical system, you can define 7 minus 4, which is 3 pi terms to, you know, what they call, you can define 3 pi terms to get the solution of form some function which is not the original function, some different function of 3 pi terms, pi 1, pi 2 and pi 3 equal to 0. So this will become your solution. And these 3 pi terms, they should be independent of each other and they will be dimensionless. So that is what Buckingham Pi theorem says. Sometimes these pi terms are called as repeating variables also, but let's not go there. That confuses me only, so I can't tell you that description. But what I have understood from this is that you define 3 pi terms which are independent of each other, which are dimensionless, and they will give you the solution for this system of physical system of equations. And one pi term will be dedicated to the dependent variable. So here in our problem there is dependent variable which is force, right? So one pi term will always have force in its formula, and remaining pi terms, here are remaining 2 pi terms, but in some problems there can be more remaining pi terms, and they will be for independent variables. So now you may ask me, sir, there are only 2 pi terms and there are 6 independent quantities. So how do you choose which variable or which independent variable goes to which pi term? So there your knowledge of the physical problem comes into picture. If in some problem, if the viscosity is important, then you take one of the pi term for viscosity. We'll solve one problem and then you'll see. But in some problems, if you see that density is important, then you take one independent pi term for density. So just hold on if you have any doubt. We'll solve one simple problem. Let's say we take one question. So the question is, there is a tank like this, and there is a ball in the tank, and the tank is filled with the fluid. Let's say water or any fluid, doesn't matter. The ball is going down the fluid with certain velocity, let's say constant velocity u. And so when the ball goes down, it will experience its own weight, which is mg. So basically, it will also experience some buoyancy force, which will be in upward direction, right? and some drag force. So drag is nothing but opposition by the fluid to the motion of this ball due to its viscosity. So let's say this is a ball of mass m. So now this problem is given, and here uh, you know we like it is given to us that this drag force, which is Fd, is some function of uh, velocity of the ball, diameter of the ball, and density of the fluid and viscosity of the fluid. And now we want to find the pi terms, or let's say we want to find some like we want to do the dimension analysis to get some idea into what is going to happen here. So now here your drag force is the dependent parameter, and these are the independent parameters. These are 4 in number and this is only 1. So therefore and fundamental dimensions will be only 3 here, because as we have seen earlier also, ud, mu, rho, they all have only mlt in their dimensions. So total parameters 1 plus 4, 5. Total dimensions 3 mlt. So therefore number of pi terms becomes 5 minus 3, which is 2. And we know that as I said earlier, one pi term will go to dependent variable. So out of these two, one pi term for drag force, which is dependent, and one pi term for independent parameters. Now, uh, now, okay, we understood this much. Okay, so now.
How to know, sir, the what is the independent parameter that
Yes,
that
yes, understood. That is why I've taken this question. I'll see, I can give you some examples and you can solve them, and the class will get over. But that is not the main thing of this discussion. And the question that you asked, I'm very happy that you asked. That means you are paying attention. I'll tell you which independent parameter we need to choose, and that depends on the physics that you are studying. So before that, let's just do some basic maths. So the first pi term, let's say, and this repeating variables. So like here we need to form one dimensionless group from the independent parameters. Uh, yeah. So typically, like, I mean, like we need to form one dimensionless group from u, d, rho, mu. So there are many options, right? But let's say we choose mu, u, and d. So now, what are the dimensions of mu? Kg per meter per second. What are the dimensions of u? U, which is velocity, meter per second. And what are the dimensions of d? Only L. So, hmm. Yeah, I have written it wrong here. Forgive me for that. I'll just rewrite it. This is not the way to do it. So yeah, coming back to your question, Pradeep, let's say we choose density as the independent parameter. Okay, we can choose anything, uh, but let's say we choose density. So now there are like, if you choose density, then the remaining three variables are u, d, and mu. So what the Buckingham pi theorem says is that, let's say for this pi term, we will call it as pi 1. It will be dimensionless, but it will be function of the remaining parameters, which are u, d, and mu multiplied with the fd, because this is the dimensionless uh, term for fd, and there will be some unknowns. So there will be a, b, and c, let's say. So this will be your first pi term, and second pi term will be pi 2. It will be again same, repeating variables are your u, d. Maybe I can take some another these things, exponents, so that it should not cause the confusion. Let's say x, y, z into density, because you have chosen density as the independent parameter here, right? So now if you do this way, now your job is to find ABC, the unknowns are x, y, z. First we'll go for the pi 1. So pi is dimensionless term, so it will become m0, l0, t0. Velocity has the dimension of L t power minus 1 raised to power a. We'll solve the pi 2 later, okay? Then the diameter has only length dimension raised to power b. Viscosity has m, L minus 1, t minus 1 raised to power c. And force is nothing but mass into acceleration. So it will be kg meter per second square. So m, L, t power minus 2. Okay. So now you solve the RHS like we did earlier. So if you only consider m terms, or maybe I'll not skip the terms because that may cause confusion. So it will become L t power minus a, L power b, mc, L minus c, t minus c, and this remains as it is. And now you club the terms together. So m terms are having c plus 1, L terms are having a plus b minus c plus 1, and t terms are having minus a minus c minus 2. Okay, and this is same, m power 0, L power 0, t power 0, since it is a dimensionless pi term. So now you compare the powers, comparing the powers of m, L, and t. So for m, what you get? This side is 0, c plus 1. So that means c is minus 1. So this is one thing you got. For L, it is again 0 equal to a plus b minus c plus 1. So c is minus 1. So this gives you a plus b equal to minus 2. And if you compare powers of t, what you get? 0 equal to minus a minus c minus 2. So therefore, we know c is minus 1, right? So therefore, a is c minus 2 and c is minus 1. So a becomes minus 3. Then if you put it back, this value in the a plus b wala formula, what it gives you? Minus 3. So b is 1. Okay. So therefore, your pi term becomes a is your minus 3. So this is u power minus 3, d power 1, mu power C is minus 1. I think I did one mistake here. Let me just check, okay? So A becomes, yeah, so see here I missed one minus sign. So A is minus C minus 2. So minus C minus 2 if you do, then it becomes minus 1. And if you put it there, it becomes minus 1. Yeah. So all three are minus 1. And then your FD. So basically, pi 1 is FD divided by mu U D. Okay. So this is your pi term. First pi term. And second pi term, since you choose density, your second pi term becomes pi 2 becomes u to the power x d to the power y u to the power z into rho. So same process you have to repeat. So this is m0 l0 t0. This is again l t power minus 1 raised to power x, l power s to y, m l minus 1 t minus 1 raised to z. Density will be m l minus 3. So if you solve this system of equation, what you should get is, I mean, I can do that, but since it's a repetitive thing, I'll just skip the thing for the sake of time. So if you do this, what you should get is pi 2 as rho u d by mu. So basically, your x equal to 1, y equal to 1, but z equal to minus 1. So this will be your solution, and it will be there. If you solve it, you'll get it. So this is your second pi term. So then what Buckingham pi theorem says, that there will exist one function like this, and if you put pi terms here, so this is fd by mu u d comma rho u d by mu equal to 0. And then since fd is our dependent variable, we take it out of the equation, and we write something like fd by mu ud is some another function of rho ud by mu. So g is some another function. Maybe if it is confusing, I'll just use f double dash. So 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 basically, now what you do some experiments, and you get this ratio fd by mu ud, and rho ud by mu is very famous ratio, which is called as Reynolds number. So here, based on the Buckingham pi theorem analysis, we understood that if we take density as the independent parameter here, our drag force will be function of, therefore our drag force will be function of mu ud and Reynolds number. So now you do some experiments, and then you find the constant of proportionality, and you'll get the, and also this f double dash that you can calculate from the experimental data. But you get the relationship between independent variables and the dependent variable. Now coming back to your question, Pradeep, why did we choose density as the independent parameter? We can choose some other parameter also, right? So let's say we choose density, viscosity as the independent parameter. If you do that, what happens? Then in that case, your phi1 term will become rho u d, some unknown powers, into fd, and your pi2 term will become rho u d into mu. Understood? So if you do that, I mean, I can do that, but the thing is, if you do this analysis, you'll get pi2 term as, again, I think it becomes same, rho, one second, rho ud by mu only it will get, but your pi1 term will become fd by rho u square d square. So you will get this is again Reynolds number. So here, from here, you will get your fd will be your fd will be some function of rho u square d square, or maybe I should write it outside, rho u square d square and some function of Reynolds number. So now you can ask one question that, okay, we did all this maths and you are getting like two different relationships for fd. It will not be exactly equal. There will be some proportionality constant. So that's why I'm writing it this way. So now which is the correct? Does equation 1 is correct or does equation 2 is correct? That is the natural question that should come to your mind. So the answer is both are correct, but it depends. So you got the different equation because you chose different independent parameters, right? So for equation 1, your independent parameter is density. So like if you choose density as independent parameter, this means the motion of the ball is inertia dominated. So what is mean by inertia dominated? That means the ball is actually moving with higher velocities. So this will happen when your Reynolds number will be very high. So like when this ball is moving with some velocity u, if the u is such a that the ball is like moving with higher Reynolds number, in that case it is the inertia dominated flow, and there your drag force becomes it is dependent on these parameters, like primarily like on this mu ud, or maybe if you like scale it, so or anyway like this only you write mu ud into some function of Reynolds number. But when you choose mu as the independent parameter, the ball motion is dominated by viscous drag or viscous forces, let's say. So that will happen when your Reynolds number will be very low or of the order of 1. So that means your fluid is very high viscous fluid like grease or something, and you dip the or you like keep the ball in that fluid and it is moving with very slow velocity. So in that case your drag force will become function of these parameters. So basically, what I'm trying to say, maybe it is like some different function of Reynolds number. It should not be the same. So the point that I'm trying to make is, uh, so when you choose independent parameter, there only you need to understand the physics of the problem. So if your fluid is very viscous and the ball is moving with very slow velocity, very low Reynolds number flow is there, then you should choose density as your then you should choose viscosity as your independent parameter. And if you see the fluid is not that viscous, it is like like non-viscous or very low viscous kind of oil or something, in that case you need to see the Reynolds number is okay, it's very high, then you should choose density as your independent parameter, and then you should find the relationship between like then you should do the Buckingham analysis, and then you'll get the relationship between the important parameters, and then you do the experimental data fitting, and you'll get the answer. So Pradeep, is your question answered here, or do you have any doubts?
Actually, sir, I've got mixed up a little bit, sir. Like, what special treatment you are doing to density at the or the mu or the rho, sir? Actually, sorry, I got mixed up with the equations that you derived. Actually, so how differently we are treating them, but
Yes.
considering the yeah.
See, don't see, there are two ways to solve this problem that you understood.
Yes,
One
sir.
is
Yes, sir.
one is if I take density as the independent parameter here in the pi2 term, or if I take viscosity as the independent parameter, which I
Yes, yes.
did here. So I am just doing maths here after that. But that maths is giving me two different solutions, which is equation number 1 and equation number 2. But now which equation is correct, or which equation defines my motion of the ball more correctly, that depends on the assumption that we made, right? So basically, if you choose density as the independent parameter, in that case, see, your Reynolds number is rho v d by nu, right? Rho v d by mu. So in some cases, let's say you are taking less viscous fluid, like some oil or something, very non-sticky oil, and if your ball is traveling through that oil, it will have higher velocities, and the Reynolds number will be higher because it is directly proportional to the u. And in that case, your domain or your drag force is basically coming because of the inertia of the ball, or the flow is inertia dominated, is what it is called. Basically, high Reynolds number flow are called as inertia dominated, and low Reynolds number flows are called as viscous forces dominated flows. Maybe in boundary layer, again we can revisit this idea, but here what I'm trying to say is, you said na which independent parameter we should choose. So that choice depends on the uh, that choice depends on the
That assumption that you make, sir. Yeah,
yeah.
got
So
it.
physics depends on the physics. So if your problem is having some, let's say if it is a viscous dominated flow and you choose the density as your independent parameter, then when you do the experiments and when you try to do the curve fitting, it will not give you good curve fittings. So basically, you are trying to fit mathematical formulas with wrong assumptions into the physical phenomena. That will not work out. So the knowledge of your physical phenomena is also important, and that was the whole point of this discussion. And this is one of the simplified case where only two choices of independent parameters were there. So you could easily define which independent parameter is suitable for which type of flow. But in reality, there are like we can. I mean, right now we don't have enough time, but you must have seen some problems in which there are like 4 or 5 independent parameters. So there it becomes difficult to define which independent parameter is important. So then you go back to your definition of the problem. You see that okay, this problem looks like it is viscous dominated problem, and then you take independent parameter as the viscosity, like that. So that is how you should solve the problems. Because maths is there, maths you understood for one example, same maths is there for different examples. but the choice of independent parameter is the key thing here, and that's how that is why I took this problem, because it is quite neat and clean problem, only two independent parameters. Anyway, so now we are at 7:45. So I think one more important thing in this chapter is there are some dimensionless numbers. Uh, uh, so you must have seen them in the class while going through the lectures. First, we discussed here Reynolds number. Maybe I'll just quickly write them. Important dimensionless numbers. First is Reynolds number, which is inertia by viscous forces. So yeah, from here also you can see. So inertia is nothing but wherever density is there, you take it as the inertia measurement. So that is rho vd by mu, rho vd by mu. Or if it is any flat plate or anything, it is rho vl by mu. Then there is Froude number, which becomes important in inertia by gravity type of problems. So where your inertia and gravity are the competing physical forces, and it will have formula like V by root GL. Then there is I think Weber number. I think it is inertia by surface tension. So inertia, again, if you see the formula, it looks something like this. And there are other numbers also, Euler, cavitation, etc., Mach number, etc. are there, but I'm not taking them at this point. But yeah, so basically dimensionless number are important because they define, like, if Reynolds number is higher, that means inertia forces are higher compared to viscous forces. Similarly, in Froude number, if Froude number is higher, that means inertia forces are greater than the viscous gravity forces for that particular type of problem. But we will shift to the next part, which is important, which is called as this, what you call, uh, similitudes or similarities. So basically, if I ask you one question, let's say uh, I want to construct a dam, and I have finalized some design which is, some height, some length, and some dimensions for the wall of the dam, etc. But I'm not sure that my design is 100% foolproof. I want to do some testing before actually constructing the dam. So, uh, what should I do? Anybody? Pradeep?
The geometric dimension, like proportionately, so you have to take some model in the lab and then you can experiment it. Then you can
Yeah.
apply
So
it in the field. Yeah.
correct. So what you are saying is correct. So in like, see, if it is some simple problem, you can actually construct the setup and see. But if it is something like dam, or let's say I am designing a new type of aircraft, so one aircraft will be very costly, right? So if I'm not sure, the logical thing to do is create some small scale prototype or model. Actually, I get confused between these two terms, model and prototype. Anyway, so instead of constructing the big dam, you construct its small model, and then you do the some preliminary experiments on it. And then if you are convinced that, oh, okay, this model is working fine, then maybe you can think about constructing dam with your decided dimensions. But then the question comes that the model that you build, uh, will it be giving you the expected results as you expect from the actual dam? So there this similarity concepts comes into picture. So there are like, I mean, I have the simple representation for them. there are like three types of similarity as far as fluid mechanics is concerned. There is thermal similarity also, but that comes in the heat transfer subject. Here we typically deal with the first is called as, okay, I'll just give the title similarity, or they call it as similitude also somewhere. If you see this term, it is similarity only. So I used to draw this image to remember this thing. So first we have geometric similarity. So as the name suggests, geometric similarity means instead of creating a big cylinder, you construct small cylinder, but the diameter and the height of the cylinder should be reduced in the same scale, same ratio. So that is geometric similarity. Basically, only the geometric dimensions will be scaled. All the angles will be same as that of original design. Then there is something called as kinematic similarity. So I think I have told this in last class also. Whenever if I say anything is kinematic, so that means there will be similarity in terms of velocity, acceleration, etc. So there will be like velocity and acceleration, or angular velocity or angular acceleration, they should be preserved, or they should be reduced or improved or increased in the same scale. So that is what kinematic similarity is there, and this is geometric similarity. The reason I am drawing these diagrams like these two circles is, so if you want to have kinematic similarity, geometric similarity is important, or geometric similarity is must. So for if geometric similarity is not there, then you cannot assume kinematic similarity. And the next step, which is dynamic similarity. So for dynamic similarity, as the name suggests, dynamic similarity means similarity of forces, pressure forces or other type of forces, drag forces, etc. But for dynamic similarity, geometric and kinematic similarity must be satisfied, and then there are some additional criteria, such as direction of acceleration or direction of motion. All those things should also be similar in the model and prototype both. So basically this figure tells you that if you want dynamic similarity between model and prototype, geometric and kinematic similarity is must. If you want kinematic similarity, only geometric similarity is required. Dynamic similarity is not required. So that is how I remembered those things, and maybe this will help you also. And yeah, maybe I'll paste it here. This is one important thing you should remember. And yeah, we have like 5-10 minutes. You had posted some problem in the chat box. 1 second. How to see that? Yeah, so first one, like this dimensionless, the image is there. I think that you can solve now. And one problem was there, model with a ratio of 1:20, 1:20. Kinematic viscosity between Froude number and Reynolds number remains the same. I think this is assignment problem. So
last question, sir. I made marked it C7, but doubtful actually it is correct or not. So
yeah, we can solve that. But before that, did you understand this geometry, kinematic, dynamic?
yes, sir. That I understood, sir.
Okay, then again the remaining thing becomes maths, and we can do that. So the question that you are asking, yeah, so here they have given 1:20 ratios, right? So typically, what what I have seen is, mm, let's say this question is there, model with ratio 1:20, and to find what should be the ratio of kinematic viscosity between model and prototype such that Froude and Reynolds number remain the same. So given is only the ratio, length ratio, let's say, is given. Typically it is defined as LR ratio, which is model length by prototype length. So here it is 1:20. This is given, okay. Now they are saying that Reynolds number and Froude number should be same. So first we write Froude number, because Reynolds number it involves density and other things, but Froude number only involves velocity and the length. So basically, Froude number definition, if you remember, it is V by root GL, right? And G is the gravity acceleration. It will be same for both. So now they are saying that Froude number for model and prototype should remain same. So that means Vm by root Lm should be same as Vp by root Lp. Okay, and therefore Vm by Vp should be same as Lm by Lp, and Lm by Lp is nothing but your length ratio, which is 1/20. So okay, we'll put it later. So let's say this is root Lr. Now if you consider Reynolds number, which is rho V, okay, Reynolds number is rho V L by mu. So for model and prototype it should be same. So Reynolds number, that means rho m Vm Lm divided by mu m should be rho p Vp Lp by mu p. And finally we want ratio of mu m by mu p, right? So we'll reshuffle the terms so that we get that. So mu m by mu p becomes rho m by Vm Lm divided by rho p Vp Lp. Okay. So if you just separate the terms, this is rho m by rho p, Vm by Vp, Lm by Lp. Now Lm by Lp is Lr. So this is rho m by rho p. Last term becomes your Lr, and Vm by Vp is root Lr. Correct, no? So this is the case. Now the question is, what is rho m by rho p? So if we assume that they are flowing the same, dividing 1/2. Kinematic viscosity. Okay, my bad. So they are not asking mu m by mu p. They are asking kinematic viscosity. So we know if that is the case, we can just simplify it here only. So this term will go away. This will become nu m. This will become nu p, because Reynolds number is rho VL by mu or VL by nu, same, because since nu is mu by rho by definition. So here we want mu m by nu p, right? So that will become Vm Lm by Vp Lp. So Vm Vp Lm Lp. It should be L r power 3 by 2, no? Pradeep?
Right, sir. This is 1.5, yes.
Yeah, it is
1 by 20 to the power 1.5. I'm also right, correct, sir. Thank you so much.
Yeah. So, okay. Actually, there is one very good question. Maybe like if we have some time, like give me 5-10 minutes. We'll take that question and
no
we'll
problem,
close.
sir. You can take time.
Yeah, because I don't know whether I am slow or the time goes fast, but every time I'm running short of time.
Time goes much faster, sir.
Give me 2 seconds. I'll find that
No
question.
problem, sir. Take your time, sir. No problem, sir.
Maybe 152. So actually, this question is there. So here they have asked you the ratio of kinematic viscosities, right? But one question was asked in the previous engineering services exam, subjective question, where they did not ask any calculation or anything. They asked you the whole, what you say, different, like here it is LR power 3 by 2, right? There they have asked not only ratio of this kinematic viscosity or something like that. They asked so many things. So if you solve that question, I think you can solve any other question in this chapter. But let me just find that question. 73. I should have wrote it down, but yeah. Anyway, 71. Okay, 1 second. If they don't find that, I have another question here only. But let me just see. 57. 58. Yeah. So, okay. So the question is, we'll stop after this. Okay. So the question is.
But these are the questions that I have put in the chat box. That is the 2023 engineering services examination. Recent one. It came in the email, net today, internet today. Yeah, Google.
I will see it later because
No
right.
problem. I just I said just.
Yeah. Okay. So right now this question is there. I think it is 2003 ESC question. So they have given that consider Froude number as the criterion for dynamic similarity, then find scale factors for velocity, time, discharge, and there are many more factors. I'll just write them as we solve. So basically, in terms of scale factor for length. So here, what they mean by scale factor is basically same, this Lm by Lp term that we are using. So, so here they have given the condition that Froude number for model should be same, since they have mentioned that it should be the criteria for dynamic similarity. The first thing should be they should be same. So that gives you Vm by Vp. We did it earlier, here only. So Vm by Vp becomes square root of Lm by Lp, which is square root of Lr. So this was the first thing. Okay. Then they are asking, so this is the first thing that they asked for velocity. So this is the velocity scale factor. Now they are asking what is the scale factor for time. So basically they are asking Tm by Tp. So now we know that time is nothing but distance upon velocity. So here distance is nothing but length and velocity. This will become Lm by L, and same for prototype. So if you separate the terms, this becomes Lm Lp. Sorry, and V ulta हो जाएगा ना, Vp by Vm, because velocity is in the denominator. So Lm by Lp is your Lr, and Vp by Vm is 1 by root Lr. So this becomes again root Lr. Okay. So this was okay. Now they are asking discharge, which is Qm by Qp. So this is for discharge. This is for time. So now discharge is what? Discharge is nothing but this thing, area into velocity. So let's say area into velocity for model and area into velocity for prototype. Now we know area is nothing but the length square. So this will become Lm by Lp square, and then Vm by Vp separately. I hope this is clear that Am by Ap is nothing but Lm by Lp square. Since it is the area, it will be length square. So Lm by Lp is your root Lr. So this is Lr square. Vm by Vp is your under root Lr. So this becomes Lr power 5 by 2. Now they had asked for acceleration. What is the scale ratio for acceleration? So acceleration divided by model by prototype. Now we know acceleration is velocity divided by time. So this is Vm divided by Tm, Vp divided by Tp. So this becomes Vm by Vp and Tp by Tm. So we know Vm by Vp is root Lr and Tp by Tm is 1 by root Lr. So this becomes 1, and it should become 1, right? Because like dynamic similarity means acceleration should be same, otherwise the forces will be different, right? So that is also proved here. Then yeah, so then they had asked, maybe the justification that I gave is not correct. Forces may be different, it should not be same, but this AM by AP is 1. Now they had asked for force ratio. What is the ratio of force? Force is again FP by FM by FP. So now we know force is nothing but force is nothing but mass into acceleration, and mass is nothing but density into volume into acceleration. So if I have to write it here, and yeah, and acceleration, so mass is density into volume and acceleration is velocity by time. Okay, so if you combine these things, so density will remain like this, but volume is nothing but L cube, because L is length scale and volume is like that, and V by T, let it be like this only. So here it will become rho m Lm cube into Vm divided by Tm, and for Fp it will be ulta, so it will become Tp rho p Lp cube Vp. Okay, and when you simplify this, it is rho m by rho p Lm by Lp cube Vm by Vp and Tp by Tm. And they had mentioned that same fluid flows through model and prototype, so this becomes 1 into Lm by Lp is your Lr, so this is Lr cube. Vm by Vp is your root of Lr. Tp by Tm is 1 by root Lr. So basically force ratio is cube of Lr cube. Then then they had mentioned what is the scale ratio for work. So now we know work is force into distance. So F into L. So work model, work prototype, Fm by Fp into Lm by Lp. Fm by Fp is Lr cube and Lm by Lp is Lr. So this becomes Lr power 4. And final thing that was asked was scale ratio for power. So we know that power is work done per unit time. So power ratio is PM by PP is work ratio and time ka ulta. So it will become TP by TM here. So Wm by Lr power 4 and TP by Tm is 1 by root Lr. So this becomes Lr power 7 by 2. So yeah, this so this is the final conclusion, and this was actually one of the very interesting question that I came across, because see here they have asked everything, right? So if you understand this, maybe you can go back and see the calculations again. Maybe because of the time I am going slightly faster, but if you understand this, I think you can solve any questions from the dimensional similarity part, because they have covered everything: velocity, time, discharge, acceleration, force, work, power. So I don't think anything other than that outside of this can be asked from this question. Maybe instead of Raudi number, they will give you some other number like Weber number. So there you have to see what is the formula for Weber number. Weber number is nothing but inertia by surface tension, right? So rho v square L by sigma. So there they will give you some additional information, and from there you can get the this same scale ratios for time, discharge, acceleration, force, work, power. Okay. Any doubts, or should we?
No, thank you, sir. Thanks. Great, sir. It is fantastic.
Yeah. Okay, then we'll stop for today and see you next Tuesday.
Okay. Good night, sir.
Good night.
Thank you so
Good
much.
night. Thank you.